Hey guys, welcome to the MakeIt Labs CAD CAM class 2017. This is just a quick overview of the class project so you can make sure you're on track. The slides talk about importing the project files that I provide, and when you do that you're going to have a few of these files here in your data panel. You're going to have the opener model, you're going to have this monster jaw model, and you're going to have something called fixturing cam starting point. This one that's the starting point is the file that you should use as the beginnings of actually completing your class project. I have copied that to a separate file just so that I'm not disturbing the distributed file. But first of all, I just want to show you a couple things about the model. So this is something that I actually designed myself. Took a few iterations to get the opener geometries just right, but there's a few things about this design that make it manufacturable or machinable with the tools that we have in that kit. The main point is that this inner radius here can be made with a 1/4 inch end mill, and it's not a pure slot. It's a little bit bigger than a 1/4 inch. But there's a couple caveats about that that we're going to get into when I show you my cam on that. Basically, if you do roughing, when we do an adaptive clear, you can't leave too much stock because this is not very much larger than a 1/4 inch. So I'll show you that in a few minutes. But this model takes advantage of some of the stuff we talked about in the homework one, where I defined the stocks based on the model. Rather than just using boxes defined in the cam, we actually draw out the stock, or model it rather, in the modeling section, and then use those as stock definitions. So for setup one, obviously the stock is just a chunk of aluminum, a rectangle, or box rather. So that was easy to define, and I've got that predefined in this model for you so you don't have to go through that exercise. But you see the opener is embedded inside the block, basically biased towards the top. This section at the bottom, this margin, is basically what's going to be held by the soft jaws. And then when we flip the part over, this is really the one that's not possible to model just using the basic stock definitions in CAM. So this is basically the bottle opener flipped over with that extra material represented on the back. And this is exactly what it will look like as we go into setup 2 after we've taken it out of the vise from setup 1. It's a little bit annoying to have to manage like these two copies basically of the model, and you'll see that as we get into the cam a little bit. It's a little bit frustrating. There's probably a better way to do it, but this is the way I've found so far that works. So you could open this up and take a look at it, but this model is linked into the file that we use for cam. You don't really need to work directly with the model itself, so I'm going to close that out for now and not save any of the changes I just made. So like I said before, I copied over that file that I provided into a secondary file, and this is the file that I'm actually using to do all of my cam work. So you can see I've already got this all completed here. This is actually the cam that was used for the in-class demo that I did Monday night. So the first thing to take a look at, we're in cam mode, obviously. It's very important or worthwhile to open up the model where this component is defined, and this is something you're going to have to do kind of constantly as you work on this, as you go between setup 1 and setup 2, which is enabling and disabling the two different models, because it's basically just two copies of that opener model that are imported into it, and flipping them on and off is sort of necessary. And you can even expand these further and turn on the definitions for the stock within each one of those. And one thing to note, it's showing up transparent here. I actually modified my opener model from the version that gets distributed, and all I did was turn on opacity to 50% on the stock model for each one. It makes it a little bit easier to see in certain cases, but we don't necessarily have to have that turned on. So what I want to do is just kind of show you, as you import this thing, the way I distributed it, the setups were all defined. So there was a setup 1 that was defined and a setup 2 that was defined. And your job from that point was basically just to program in the operations. But I kind of wanted to just give you a little bit of background on how those setups are done. So for setup 1, obviously we're starting off with that chunk of aluminum. That stock is defined as a body, and that body was defined in the cam, and it was the upright version of the model, or the initial copy of the model with the part in this orientation, and it was just pointing at the stock definition that was the box in that copy of the model. It's a little bit confusing, I know. The work coordinate system for both setup 1 and setup 2 is this corner. This rear jaw here is the fixed jaw in the vise. And for both of these, we're using this corner. So we're going to touch off on this face, and we're going to touch off, it's a little hard to see it here, we're going to touch off on that face, and then we're going to touch off on the top of that. The nice thing is that both setups use the same work coordinate system origin, so that we don't have to retouch off when we flip the part over. That's one of the benefits of this work holding setup that I defined, just to make it a little bit quicker to run the part in class. So that was setup 1. Setup 2 is defined also in this model. And this one uses, this is where we get into that point where we need to flip these things around here. This uses the flipped version of the part, and it uses the setup 2 stock that was defined. So this is exactly what it will look like. It'll be held in the soft jaws, and we'll have this remaining material on the top that we're getting rid of. That's really the whole point of setup 2 in this particular job. Oh yeah, I wanted to also show the work coordinate system for setup 2. Again, it's that same point. So, all right, before we get into the actual operations that I have programmed here, I kind of just wanted to show the tools that I have set up. This was the homework, I think, in the second week, just asking you to set these tools up. Should have 5 tools. They need to be numbered in this order because I really want everyone going through this in the same way so that I can more easily sanity check people. There is not necessarily any reason you couldn't number them differently, but for the sake of consistency in the class, I want them all numbered this way. So tool 1 is that 1/2-inch flat end mill. I actually defined mine a little bit with more detail than you guys necessarily have the info for. This shows where they came from, what the model numbers are. Got the actual flute lengths and shoulder lengths and everything programmed in here. If you really want to match this, you can. I'll probably provide this document shortly. I defined the tool holder as a Tormach set screw holder. I did rough in some feeds and speeds. It's a little conservative. I just set in 4th thou per tooth and 4,800 RPM just as a rough starting point. And in the post processor tab, the most important thing is make sure that this was set up as tool 1. This is a common dialogue you're going to get if you make changes to your library, that it says, hey, all these operations use this tool. Do you want to update them with the settings that are in this tool definition? This gets you in trouble all the time because it defaults to yes. You really don't want to make any changes here. So generally you want to say no. If you have speeds and feeds programmed that are different for each of the operations that use this tool, it will basically go and blow those away and replace them with what's in the tool library. So that's a trap that I have gotten into before, and I see a lot of people accidentally just say yes right through that. So you're going to want to say no to that. Just quickly go through the rest of the tools here. Tool 2, it's a 1/4-inch end mill. This also has the MSC info where the tools come from, you know, the shaft diameters, the lengths, all that stuff. This tool happens to have a larger shank than the actual cutter. Just happens to be the tool that I purchased for the class, so you can actually match that definition if you want. It actually required using the more detailed tool editor to get that set up. This is also in a set screw holder. I just did an initial 2,000 per tooth, 5,000 RPM, just as a rough starting point. And the post-processor page, you got to get all these numbers set up for tool 2. And again, no, we don't really want to change that, or just cancel out of it. It's fine. I'm not really editing here. Tool 3 is that 1/4-inch spot drill. High-speed steel. You know, this is all the info, again, from MSC where the tool came from. Cutter diameters. It's going to be held in a TTS ER20 collet holder. Feeds and speeds. It's really the vertical feed rates that matter in this one. I just have it roughed in at 3,000 and 3,500 RPM. Post-processor, make sure it's going to be set up for tool 3. Tool 4 is the number 9 drill. There's the info for that. The holder, we have only one drill chuck set up in the default Tormach tool library. We actually have some different chucks at MakeIt Labs, but it's fine to define it as this for now. Speed and feed, the vertical is what matters again for drilling. I've got it set for 4,000 feet per revolution. Post-processor, again, make sure this is set up as tool 4. The 5th tool is the 1/4-inch chamfer. The only real trick on this one is that if you define it as a chamfer mill, it needs to have a diameter of the tip. This one I think I bought for the class actually does have a slight flat on the tip. I just define it as 1,000 at the end. Taper angle is 45 degrees. And we're going to hold that in an ER20 collet holder. Speed and feed, I've got it set just under 1,000 per tooth and 5120 RPM, max RPM. Post-processor, just make sure it's set up as tool 5. So you should have your tools basically set up in a similar fashion. Doesn't have to have every last field filled in the exact same way that I did, but they need to be close to that. I'm going to cancel out here. And we're going to go through the operations kind of as I decided to program them. So, initially, we need to face off the top of this material. So, if you highlight the setup, you can see what the stock looks like. So, just to refresh your memory, we're working from the full chunk of aluminum. First thing I'm going to do is face off the top here. And we can edit this operation and see. So we're going to face that off using the 1/2-inch flat end mill. Just using roughed in feeds and speeds for now. This is actually what I ran it as in class, but I will try to do another video where I show going through the speeds and feeds thinking, basically, and how to look at these in a little bit more detail using HSM Advisor or other techniques, but these numbers work. The geometry, I'm actually just using stock contours with nothing selected, basically saying, hey, clear off all that material down to the top of the part. The heights pretty much work by default. Passes and linking, you don't need to make too many changes in there. And it generates a tool path that looks like that. Next, this is kind of the first and really the bulk of the machining that gets done on this entire part is roughing to clear away most of the material that leaves most of the bottle opener, and then we just have to do some cleanup after that. So this is an adaptive using, again, the 1/2-inch, using speeds and feeds, kind of as you see down here. Again, I'll go through that in detail in a different video. The geometry, I have selected the bottom of the model. So that's automatically going to set things like the depth of that cut without you having to go through and explicitly do it. If you can also choose the top geometry since it's the same shape, but then you have to go through and separately tell it the bottom height, where that is. But if you choose the bottom, it tends to do the right thing. In the passes tab, this is where we have to pay attention to a couple of different things here. So, first of all, optimal load is a critical setting. It's basically the optimal width of cut that it's going to use for an adaptive clearing. It's trying to calculate it so that it's always keeping that much material in the cutter. I'm doing 75 thou in this case. That's kind of getting towards the capacity of the machine. When you heard the cut run, you could tell that it was actually working fairly hard. We're taking a fairly aggressive, we're cutting at 38 inches per minute, and we're taking 75 thou, and it was making those all those concentric passes to remove that material. It's for the Tormach machine. That's actually it's not as aggressive as you can go, but it's relatively aggressive. You could move material a little bit faster if we had a 3-flute end mill that was made for aluminum, but for the 2-flute that we've got, this is a reasonably aggressive cut. Now, I mentioned earlier that there is a situation we get into in sort of the armpit of this opener, if you will, because if we leave too much material, the 1/4-inch end mill isn't going to be able to get in there when we go back and do the next step. So there's a magic number you kind of have to use for this part. It's not something that's going to apply to like every single project. It's just a number that happens to work for this design. Because we're doing this adaptive clearing as a roughing, leave some stock because we're going to go back and clean it up later with a contour. And the default value, I think, is 20 thou, and that's not going to work properly. You need to dial that down to 5 thou for a reason that I'll show you when we get to the next adaptive clearing, when we drop down to the 1/4-inch. So that's that operation. I'm just going to regenerate this so that we can see what this one goes back and does. We got the bulk of the material away with that 1/2-inch adaptive. We're going to go back in with the 1/4-inch end mill and then use rest machining so that we don't have cut air. And we're going to clean up the remaining stuff that 1/2-inch end mill couldn't get. Oops. So we're now using our second tool. We did that facing and that first adaptive, both using the 1/2-inch. Now we're dropping down to our 1/4-inch end mill. Speeds and feeds, just using the roughed in numbers, so 2 thou per tooth, 5,000 RPM. I run it a little bit higher because it's a smaller cutter. The machine can push it okay. The geometry, same geometry that we had selected for that first one. But we have rest machining enabled for this operation, and the source is set to from previous operation. So it's going to look back at that last operation that got run with the 1/2-inch and figure out what material got removed from that, and then only calculate tool paths to remove the material that operation couldn't clear away to reach the geometry that we told it to. Heights by default are generally correct if you select that geometry. But again, there's a couple critical parameters in here. Optimal load, I have set down to 50 thou, and that's a reasonable number that I determined to work well with that cutter. That initially was determined with the help of HSM Advisor, and then tested out on the machine until I found a cut that was cutting happily. So it does take a little bit of iteration, but you'll come to have your own kind of gut feel for this after you've done a few things and tested out the particular tools that you purchase. But so 50 thou optimal load and stock to leave. Again, we have to dial this down to 5 thou just to get this part to work properly. So what will happen if we left stock to leave at the default of 20 thou, even the 1/4-inch end mill wouldn't be able to come in here and do an adaptive clear. You see what's really going on? are all these little tiny paths for it to get in there and clear out this material. If we had left 20 thou of material stock to leave on these two adaptives, there would be a large amount of material still left over in this corner. And for the next operation, when the contour comes in there, it's just going to happily come around the corner and then plow into this huge mass of material that hadn't been removed in the roughing steps. And it doesn't know any better or care any better, so that's an opportunity where you can easily break end mills. So it's something to pay attention to on your own projects going forward when you have a feature like this, just to make sure that you're generating toolpaths that clear away the material during the roughing phase, so that when you go back and do a finish pass later on, that you're not plowing into a bunch of extra material. Simulation can help you see that problem before it happens, but I have broken more than one end mill because of that kind of thing before. So the next operation, again using that same 1/4 inch end mill, is a contouring operation. This is really our finish pass to give the whole outer edge of this part a nice finish. I'll quickly take a look at that. Again, it's using the 1/4 inch, 5,000 RPM, 2 thou per tooth. Geometry is the same. We don't need to use rest or anything like that in this case. The heights by default are correct. And make sure there's no stock to leave because this is our finishing pass. And that's about it. So that basically machines out most of this bottle opener, but we need to also drill out the hole, and then we're going to chamfer it. So the next operation we're going to do here is a spot drilling. So this uses now tool number 3, which is our 90-degree spot drill, 3,500 RPM, plunging at 12 inches per minute. The geometry is really just picking that hole, or this face in this case. That's how I chose that geometry. And we'll figure out that that's the center of the hole that you want to use. Now the heights I actually programmed in this case rather than letting it choose. And this is something that you need to get a feel for over time. The bottom of the hole, I'm not drilling the tip through the bottom. I'm basically just telling it to go 75 thou below the top of that hole, the way I chose the heights here. And you can actually see the cone that it generates, so that's how far that tip is going to protrude in there. And all we're trying to do with the spot drilling is give it a little tiny cone so that the follow-up drilling from the drill bit will follow and not wander and skate when it tries to start drilling. So that's a reasonably good number you can use for that kind of thing in the future, but you can feel free to experiment and dial that up and down for different projects. And we're using just a rapid out drilling. I mean, this is really just going to tap it, and that's the entirety of the operation. It's not like it's drilling through it, so nothing really to worry about there. After we've spotted it, we're going to come in with the actual drill, running this at 3,000 RPM, 12 inches per minute plunge. The geometry is, again, that hole face. And the heights, in this case, are programmed both to the bottom height in particular is to drill the tip through the bottom, and we're going to offset it and go in another 10 thou here. So it's a little hard to see, but you can see that the point of this is drilling through the bottom. You know, there's that extra material that's hanging out that we're holding onto it by, and it's going to drill into that a little bit and poke the tip all the way through. You have to worry about this depending on your work holding. In some cases, you know, you might be accidentally drilling through your parallels or something like that. You just got to pay attention to that kind of thing when you're programming it and thinking about your work holding. But in this case, this will work. And I'm doing a chip breaking partial retract. So this will stop and very slightly bring the spindle up every so often. Programmable parameters in here. I'm using the defaults. They tend to work okay. This will just help break the chips. This isn't a particularly deep hole, but it pays to be a little bit conservative. Breaking up drill bits in your part is no fun. So then our last operation here, for setup 1 anyway, is to do the chamfer. And we're using tool 5 for that, which is the 1/4 inch 45-degree chamfer mill. Running this at the max RPM, and we're cutting at 15 inches a minute. It's basically just under a thou per tooth. The geometry, I've selected both the outer contour of the part plus also the hole. Heights you don't necessarily program the heights explicitly. The thing that actually will change how aggressive that chamfer is are these two parameters, the chamfer width and the chamfer tip offset. By default, I think this is what they come up as, 20 thou, and that makes a fairly nice broken edge. But if you look at these, they describe exactly what those two numbers mean in terms of the geometry. It's just controlling where it's putting the chamfer tool along the edges that you've defined in the geometry setting. So we've got setup 1 basically defined here, and it's nice to be able to run that simulator and see what we're going to do. So when I run the sim, I always turn the stock on because that's really kind of what we care about. I'm going to turn the toolpath off just for clarity in this case. The controls down at the bottom, obviously you've got your play, you've got your, if we just hit play, we can see what it's doing kind of in real time. You can speed that up and slow it down with this, and you can actually make it go backwards, which is kind of bizarre, but if you've already simulated a particular operation, you can just skip over it with the go to next, and if you want to see what the end result of all of the operations are, you can just click to the end and see what you're left with, and that's another useful thing to do. But we can see that this is now doing the adaptive clearing. It just did the facing while I was talking. Make this go a little bit faster here. So you can see it's leaving all this material in here because it can't reach it, but it can clean this up, and it's coming back and it's doing these moves where it actually picks up the tool and drops it back down because it's always trying to do climb milling. It doesn't want to go back and forth because it's we told it to just do climb. So you saw that 1/4 making all those really, really small motions, but you can see that it cleared out almost all the material in there so that this contouring operation was able to get in there and not encounter a huge chunk. You saw the drilling, the spotting, and now this is the chamfer operation. Now I didn't model the chamfers in the CAD. I didn't really see the reason to. I'm just doing these as edge breaks really. But when you simulate it, you get into this weird situation where you're like, well, I saw the chamfer tool run through it, but like, why is there all this gray crap? And the reason is that it's fighting basically between showing you the stock that you told it to show you and showing the model. So if you shut the model off temporarily when you're running the simulator, you can actually just see the stock just like you would on the machine. And you can see that there's now a chamfer in there. It's a little faceted because it's not running at the highest level of accuracy, but that's what we get left with at the end of setup 1, and that's exactly what we're looking for. So now let's take a look at setup 2, and we'll switch to the second setup here. This is just like in the CAD section where when you are switching between components, you need to select using that little radio button. You need to do the same thing here in CAM. So you see we flipped the part over. If I've got that setup highlighted, it shows you the stock definition in yellow. If I shut the actual model off, you can see that the whole thing is modeled down here in yellow, because this was all something we defined in CAM and pointed CAM to and said, use that as your stock definition. So we're not doing a whole lot in setup 2, where basically the whole point is to get rid of all of this material. So the first thing we're going to do, I chose to do an adaptive clearing to kind of get rid of all that overhanging material, because you can get into a situation where if you just face that off as it gets closer and closer to the part, you're getting it down to basically tinfoil. So after considering a bunch of different potential ways to do this, I decided to do an adaptive clear, which basically gets rid of most of that overhanging material, and then we go back in and face it. So we're going to use our 1/2 inch flat, running with the same kind of cutting parameters that we were using earlier. You could probably make this a little bit more aggressive because we're removing we're taking a much lighter cut in terms of depth of cut, but just for the sake of clarity, I use the same speed and feed parameters. The geometry, I have a chain selected here, which is just the outside, and it knows that I'm trying to remove all the rest of that stock. Heights are pretty much just default. Nothing particularly special set under the passes, but the optimal load actually is one thing to pay attention to. I did take a slightly more aggressive cut, actually, now that I think about it, because I think we did 75 thou in the first setup. This is a little bit, like I said, a little bit thinner depth of cut. So I upped the optimal load to 100 thou, and it seemed to be perfectly happy with that. So it'll go a little bit faster. And there was no stock to leave, nothing like that. We're just roughing and getting rid of most of this material. Then come back in, and we're going to do facing to get rid of the remaining material. This will be a little bit more clear when I run the simulator. Same feed and speeds. The geometry, nothing is selected. We're basically just facing it down to the top of the model. I do multiple depth passes just because it's a reasonably thick chunk. I think it's 150 thou. So I told it to do no more than 70 thou step downs. So it just breaks that up into a number of different steps. And if we look at that, that's what it's generating as a toolpath. So the first adaptive clear is going to get rid of most of that. Then this is going to come in and just do facing, and it looks like it took 3 passes to do the facing. We're going to finish off setup 2 with a chamfer. This is just like in the first setup. I'm going to use tool 5. These parameters for speeds and feeds. The geometry is just this top contour plus the hole. The heights are default. We're going to also do 20 thou and 20 thou for the width and offset. And we will run the simulator just to see what this does. So again, we've got the stock turned on. I'm going to shut the part model off just for clarity and run it. So we see that it's doing this adaptive. It's clearing off most of the overhanging material. Now there's still a little bit of overhanging material kind of in this area, but it turns out it doesn't really matter. And now it's doing the facing. First pass. Second pass is a bit more aggressive. Finishing pass. Now it's chamfering. And we're done. And there's our bottle opener. All right. Hope that gives you guys a pretty good overview of all the things you need to do to get the class project in shape. We will be looking at that as you come in pairs to run your project, and making sure that everything seems to be set to go. We'll basically be going through both of your cams at the same time and just having a discussion, and just we'll all double and triple check to make sure everything looks good. Then we're going to post-process that code and load it over onto the machine, and you're going to run it. So if you've got any questions in the meantime, bring them up on the Slack channel, and hope to see you within the next week or two to run your part. Thanks a lot. Bye.